Okay, we already looked at the Pacific circulation in a little bit of detail, but let me revisit it just as a preparation for one of the more exciting topics we are going to do next. That's the El Nino and La Nina. If you are looking at this course and you are maybe from early college years or so, maybe you have not heard of El Nino. But if you're already in the field of climate science, oceanography, or related fields, it's very likely, or if you live in a place like California or Indonesia or Australia, you probably have already heard of El Nino. So for preparing for that, let me re-emphasize some of the circulation features of the Pacific Ocean. We already talked about the Kuroshio, which is the western boundary current taking the warm waters from the West Pacific warm pool all the way up to Japan and off into the open Pacific. Pacific is much bigger than the Atlantic, so the impact of the Kuroshio on the North Pacific is completely and totally different than what the Gulf Stream does in the North Atlantic. This is something very important, okay? This is why you have North Atlantic deep water forming in the Atlantic Ocean in the Jin Seas, but no such deep water formation happens in the Pacific, even though you have a similar Kuroshio current and a North Pacific current. Okay, so North Pacific current, that is the extension of the Kuroshio after it leaves the coast of Asia around 30 degrees north, and on the other side, eastern boundary, you have the California current, which we mentioned already several times. In the tropics, you have the North Equatorial current, and we talked of the Alaska current, which is the subpolar gyre. The South Pacific subtropical gyre has the East Australian current. Even though it's a western boundary, it's on the eastern side of Australia, so it's called East Australian current. It is a western boundary current. Antarctic Circumpolar current, which is a big part of the Pacific circulation because Pacific is so huge and has so much exposure to the Southern Ocean exchanges. Turns out to be very important. Peru Current is the eastern boundary current in the south. It's been famous for a long time because it's very, very rich in fisheries productions, anchovies. As the Spaniards colonized Ecuador, Peru, Chile, and so on, they have been catching fish for literally centuries. It's also rich in biodiversity and so on. You have the South Equatorial current, so North Equatorial current and South Equatorial current with doldrums in the middle and the equatorial countercurrent. So this is just re-emphasizing a much better defined gyre with the North Equatorial current, Kuroshio extension, North Pacific current, the California current, so forming this subtropical gyre. You have the subpolar gyre there with the Oishio coming down, another western boundary current, and the eastern boundary current here is the Alaska current. In the Gulf of Alaska, you end up with the so-called Alaska gyre, and you have the South Pacific gyre with the South Equatorial current, East Australia current, west wind drift, Peru current, and so on. So when we looked at sea surface temperatures, we saw that the eastern part is much colder. It's 20 to 23 degrees depending on the time of the year, whereas here it's 28 to 30 degrees, so 7-8 degrees temperature difference. And we said that cold waters, denser waters, low sea level, high pressure, warm waters, more volume, higher sea level, and we said that sea level difference from here to there is about 50 centimeters. But you have to add another basic concept you've already learned, right? If sea surface temperature is cold, sea level pressure is going to be high. If the sea surface temperature is warm on this side, the sea level pressure is going to be low. So you have a strong pressure gradient from high pressure here to low pressure there. Okay, what happens? You have winds going from high pressure to low pressure. Since you are so close to the equator, you have to remember again, Coriolis is very weak close to the equator. So you're going to have strong zonal winds, westward winds from the East Pacific to the West Pacific. they are going to add to the upwelling. Remember, upwelling is happening because southeasterly and northeasterly trades are pulling the water westward. Coriolis is doing the divergence. You are bringing cold water, which is increasing the sea level pressure by cooling the temperatures. Sea level pressure is creating a pressure gradient and creating additional winds. So there is a feedback which gives you strong zonal winds which favor the upwelling. So the system obviously remains in equilibrium, but this is a temporary equilibrium. So this sea surface temperature, warm, cold. So for me it's cold, warm. For you it should be warm, cold anyway. East-west gradient in pressure, temperature, and winds and so on all change every few years for some reason that we don't totally understand. Maybe there are many reasons. The warm water that's being piled up in the west begins to slosh eastward, which means the winds that are pushing it west are becoming weaker, and this begins to create lots of changes in the weather around the world, which is called El Nino. So we'll learn later on why it's called El Nino, how this process happens, and so on. But this is the time for you to really make sure you have understood all the basic concepts and you can remember everything and invoke those concepts as needed, when needed, to make sure you are adding things properly. 1 plus 1 plus 1 plus 1. Always. Very simple concepts, but to be added carefully to build the bigger picture.